Okay, we're going to continue on here, chapter 12, I think, still, kinetics. So last time we got into sort of specific orders of reactions. We had our first order, our second order, and our zero order reactions. And again, these, as we talked about last time, are really the kind of most common. As we talked about, most reactions that you think about have, maybe one reactant, two reactant, maybe three, like what we're doing kind of today, even though really HCl is a catalyst in this reaction. So, these are the very common sort of overall orders that we get. We also saw that they do have specific sort of concentration and time equations, sometimes called integrated rate laws. So for example, first order, natural log of A is equal to the natural log of A naught minus KT. For second order, we have 1 over A is equal to 1 over A naught plus KT. And for zero order, we have a concentration of A is equal to concentration of A naught minus KT. Again, first, second, and zero order. They each obviously have some half-life equations that we talked about as well that are specific. The first order does not, the initial concentration is not taken into account for the half-life. For second and zero order, you do take the initial concentration into account, as it does have an effect on the half-life. We also talked about really some specific sort of graphs that go with these guys. So natural log of A versus time. Pretend that's a straight line. Will yield you a straight line here-ish. If I could draw it, we'll just keep making it darker and lighter. That I think is good. That gives you the straight-ish line there, which will give you where the slope is equal to minus the rate constant here. Again, our line having a negative slope, giving us a negative and negative, giving us a positive value for the rate constant. For first order, second order, we have 1 over the concentration versus time. That actually gives us a positive sloping line where the slope is equal to K. And lastly, concentration of A versus time, again, giving us a negative slope where the slope equals minus K in this case. We talked about really important also the units of the rate constant for each of these. They do help you understand sort of which sort of formulas you should be using. Typically speaking, first order, the units of K are 1 over seconds. As we talked about, it doesn't really have to be seconds, but kind of like what we did today, obviously we recorded our reaction in seconds. And usually the unit of time that we deal with, but it doesn't have to be seconds. It could be minutes, hours, days. It's just really 1 over some type of unit of time. For second order, we end up with usually units of 1 over molar seconds. Again, with the seconds here, it could be any unit of time. And for zero order, we end up with really the same units that you typically find for the rate, which is molarity over seconds. So as we talked about, there's a lot of times you will come across problems where they really won't, in flashing lights, sort of tell you which order you're dealing with, but they will give you this sort of piece of information. They'll give you the value of the rate constant. And just by seeing the units associated with it, you should be able to nail down, what order of a reaction you're dealing with, and obviously use the appropriate equation for that. We also, towards the end, got into talking about the relationship of temperature and energy and activation energy. Remember that activation energy really is that sort of hill that the reactants have to climb to get to the product side. And that should always be sort of a positive number. And this is a exothermic reaction overall here. Our reactants are higher in energy than our products, so energy is being given off. Endothermic would look opposite. You would have a lower reactant than products, right? Look something like this, where this would be our activation energy in that particular case. So exothermic on the left, endo on the right, but it really is that hill. And as we talked about, basically as the reactants are coming up the hill, they're starting to break their bonds and starting to make new bonds. And as we talked about, the very sort of height of that activation hill, that is what is sometimes referred to as the transition state. You usually have a transition state complex, or sometimes referred to as an activated complex up there. And those are really just fancy words for the idea of we have something that is partially making bonds, partially broken bonds. It's really sort of intermediate between reactants to products. Because it's very high in energy, typically where you find that, it's usually a very unstable sort of situation, and it usually very quickly sort of comes down the hill to our product side, and obviously our products are being made. So a lot of times those sort of transition state guys are very hard to isolate because they really don't hang around a very long time because they're very high in energy. We saw a couple of different sort of equations for the Arrhenius equation. One is more of a graphical equation where we take the natural log of the rate constant versus 1 over the temperature in Kelvin, and that will give us a straight line if we choose to graph it, where the slope is equal to minus E of A over R being the gas constant, which is the 8.314 version of it. We also finished up talking about basically a calculation version of that equation, which is basically this guy. I'll just steal it from the problem we did at the end there. And if you basically have 2 points, it's sometimes referred to as a 2-point version. And ideally, these would be technically 2 points from that straight line of that graphical version that you would do there. So basically, if you have 2 rate constants and 2 temperatures, you could calculate something like the activation energy. You could calculate the rate constant at different temperatures as well. A couple important things as we did talk about as we saw here, it really do want to be careful between the activation energy and R. R is in joules, and typically speaking, the activation energy is usually given to you in kilojoules. So you got that sort of conversion. You want to make sure that you do, so you're not off by a factor of 1,000. Any questions on any of that stuff we talked about last time? Okay. So I think we left off here. So why don't you give this one a go to start off with? Thank you very much. So as we talked about, if we raise the temperature, we would expect the rate to increase. So let's take a look here what the activation energy would be if we rose the temperature 10 degrees Celsius, and they give you some, I think I went right through, I think I just missed your tables, I think. Because you can use temperature 300 and 310. So give it a go, see what you come up with. So we have the natural log of K2, K1 equals E of A over R, 1 over our temperature minus our other temperature there. In this particular case, they gave us a T1 that was 300 Kelvin. They gave us a T2 that was 310 Kelvin. And we knew that, again, that K2 equals basically 2 times K1. So really, in this case, if we kind of put our numbers in here, the natural log, putting in there that 2K1 over K1 is equal to E of A over our R, which is our 8.314 joules Kelvin mole. 1 over our first temperature, which is 300, minus 1 over our 310 Kelvin. In this particular case, we don't really know what K1 is, but since it is the same number on the top and the bottom, it should cancel out, basically giving us the natural log of 2 on the left-hand side. Natural log of 2 on the left there basically gives us 0.693 equals E of A over 8.314. And if we clean up what's in the parentheses there, we got 1 divided by 300 minus 1 divided by 310. It gets us something like 0.00010756. Math-wise, I'm going to multiply this guy to that side, and then I'm going to come back and divide by that guy, right? So we're going to multiply, then divide. So let's do that. We will end up with basically a natural log of 2. We will times it by 8 point, if I could get my thing here to work, 0.693. Come here, punch numbers. There we go. All right, then we're going to divide it by 0.00010756. gets us a activation energy of looks like 53594.7 units. Here would be joules per mole. Usually it is in kilojoules per mole, so do a little dividing by 1,000, and that would yield us approximately, call it 53.6 kilojoules per mole would be our activation energy, which would be positive in this case. Any questions on any of those steps there? So here we did again solve for activation energy, but a reminder that you really could use this equation to solve for anything that's there. So you can use it to solve for any of the temperatures. You could also use it to solve for any of the rate costs as well, depending on obviously the information that's provided to you. Any questions on using this equation here? So as we did talk about last time as well, again, when we do increase the temperature, basically what we're doing is adding energy to that reaction, and thus we are creating a greater proportion of molecules that have enough energy really to get up and over that activation energy hill. The result of that is we typically will see the reaction rate increase because there's more guys that can actually get to the other side quicker. Vice versa as well, that we talked about, that if we ended up kind of throwing everything on ice, we would be like removing energy from that equation. That would lower the proportion of molecules that really do have enough energy to get to their side. The result of that would be we would see obviously a slowdown in the overall speed of that particular reaction. Any questions on temperature relationship here? Okay. So as we talked about before, there is the idea of collision theory, which, they do have to hit each other in order for reaction to take place. But as we also talked about, they have to hit each other really with the right amount of energy and really in the sort of right location. So when this guy comes through and collides with our purple guy here, that is the right orientation, going to allow those guys basically to stick together, and we will get products formed. We have the same sort of collision, but it's really the carbon side that kind of comes in. That is really not the correct side of that reaction. So it's just a reminder that, sometimes people think all you need is, for them to basically come in contact with each other, and it's guaranteed that you are going to basically form products. But there really is two important aspects of that: right amount of energy and really right location where everybody collides with each other in order for products to actually be formed. Another really important idea is pretty much this, which is kind of very similar to the idea of Hess's law. If you remember, Hess's law is like when we take a bunch of little reactions, right, put them together to make a big reaction, right? And the idea behind that is sort of what we're going to talk about here. Not all reactions, for example, run directly from reactants to products. Sometimes it does happen in sort of multiple steps along the way. So for example, maybe we had A plus B made C plus D, then C plus D came together to make E plus F. And if you add these guys together, you can cancel out whatever's on opposite sides, and we get our overall reaction here that we're looking for. So not all reactions, basically a one-step process. Sometimes it does happen in multiple steps. And reaction mechanisms are ways in which we try to predict a possible pathway for how a reaction takes place. And again, it may require multiple steps to do so. So the overall progression of a chemical reaction is represented by what are sometimes referred to as elementary steps or elementary reactions. And these are sort of the individual reactions that when you put them together, basically give you the overall reaction that you're looking for. The sequence of elementary steps do lead us to this product being formed. So for example, when we run this reaction, while this reaction is happening, N2O2 is detected. But clearly, if we look at the overall reaction, there is no N2O2 present. So what that implies is because it is sort of seen during the reaction here, that implies that it is made, but by the time the reaction is done, it is pretty much gone. So it is sort of like an intermediate along the way. It gets made through the production of these steps and then basically is completely gone at the end. So if we could propose a sort of mechanism, which is what we see here, where the first step, maybe a couple of NOs come together to make the N2O2, which would explain why it's seen during this reaction, followed by that N2O2 reacting with oxygen to make our NO2. And by adding these together, these guys would cancel. Again, anything that is on opposite sides of the arrow, that's the same, will completely cancel or can reduce down as well. And what we're left with is everybody on the left stays on the left. So 1 and 2 NOs, 1 O2, and 2 NO2s on the right-hand side of the arrow. So mechanisms try to explain how reactions actually proceed. They are plausible explanations for that. Does it always mean that it will always happen via the same mechanism all the time? It doesn't, but it does try to explain sort of, how it sort of takes place. And that does bring us to intermediates, and intermediates are important because intermediates, as I mentioned before, are things that do appear early on in a mechanism, but they get completely used up by the time the reaction is over. So you should never find an intermediate in the overall reaction. If you do, then it's really not an intermediate in that particular case. And that's what we see here with the previous example. The N2O2 gets made on in an early step, gets completely sort of consumed in a later step, and it again is nowhere to be found in the overall reaction. When we look at each of these sort of elementary steps, we can describe them as unimolecular, bimolecular, or termolecular. Uni meaning basically one molecule is involved, bi meaning 2 molecules, and ter meaning that there are 3 molecules involved. And each of these elementary steps up here would be bimolecular, 2 guys involved, 2 guys involved, and each of those steps would be a bimolecular reaction. Now, if you remember when we wrote rate laws, for example, that when we figured out the orders for everybody, they were not the coefficients in the balance equation. They actually came from basically experimental information. So the one place where you can actually write a rate law and use the coefficients in the balance equation is actually when you are doing mechanisms. So when you're doing mechanisms for elementary steps, you actually can use those coefficients to write rate laws. And that's really helpful and beneficial to help you determine whether or not a mechanism is a kind of good mechanism or a bad mechanism. So when we look at elementary steps such as these things, we can actually use the coefficients to write a rate law for each elementary step. And that's where we get these rate laws on the right here. The coefficient is 1 here, so it's to the 1. Coefficient each of those guys is to the 1, and then obviously this is the same thing as 2a basically, and again that is where the 2 comes from. So this is really the only place in sort of kinetics where it is acceptable to use those coefficients as the exponents or the orders, if you will, in the rate law. Now there's a couple really important things, and very often the question is, is this a plausible mechanism for this reaction? So is this possibly how this reaction basically takes place? And you're going to basically determine yes or no in that case. So there's a couple really important things that you really need to make sure of in order to make that determination of, is this sort of a good or bad mechanism? The very first thing is pretty straightforward. When you take all the elementary steps and you add them together, you cancel out anything that's intermediates. Obviously, the reactions need to add up to the equation that you're looking to find, basically. So if you had like A plus B goes to E plus F, and you add up all your things, you get A plus B goes to D and C, that is not a good mechanism. Those steps did not add up to the reaction you're looking for. The other really important thing is the rate determining step, which is sometimes referred to as RDS, for rate determining step, should have the same rate law as the one that has been found experimentally. So what is the rate determining step? The rate determining step is the slowest step in the entire mechanism. It is really the one that determines the overall rate for that reaction. It's kind of like the guy with 400 items in the 10 items or less line, right? You got to wait for them to go through before you could get through, sort of the rate determining step. Same thing here. There will be a rate determining step, and we'll talk about how you can identify that in just a second. But when you look at the rate determining step, which is the slow step in the mechanism, and you write the rate law, it should really match the one that was found experimentally. So very often in these sort of mechanism problems, they will somewhere in the problem say the experimental rate law was found to be this, or the observed rate law was found to be this, and they'll sort of give you that information. And the step in the mechanism that matches that perfectly is basically your rate determining step and the slow step in the mechanism. Any questions on that so far? So these are the steps. Obviously, you can measure the rate of reaction, formulate a rate law, and come up with a possible mechanism. So let's take a look at a couple of things here. Let's take a look at, why don't you try this first and then see what you come up with. The experimental rate law for this reaction is the rate is equal to K times NO2 squared. The reaction is believed to occur through these two steps. What is the overall reaction we're looking at? What is the intermediates? And what can you say about step 1 and 2? So why don't you take a few moments to see what you come up with on these. Okay, let's take a look. So start the first one, which is what is the overall reaction here? So all we need to do is basically add them together. In this case, I got NO3 on the left and NO3 on the right. That's going to cancel. I got a little NO2 on the right and NO2 on the left that cancels. I think that's all that cancels. That leaves us on the left-hand side, NO2 plus CO. On the right-hand side, we have NO plus CO2. Here would be our overall reaction. Any questions on that one there? The intermediates would be, so NO3, what about NO2? Is NO2 an intermediate? NO2 is actually not an intermediate because it is still found here in the overall reaction. So remember, the definition of intermediate is something that's made early on and gets completely used up, which means it should not appear. So although we did reduce down NO2, it was still there at the very end, which would imply that it's not an intermediate. So the only intermediate here would be our NO3. Any questions on that one there? Now, we can, for each of these reactions, or each of these elementary steps, write a rate law. So if we wrote a rate law for the first step, the rate would equal K times NO2, and it would be squared. Again, there's basically two NO2s there, right? 1 and 2. We can then do, for the second step, the rate is equal to K times NO3 and CO in this particular case. Again, just the reactants and the rate laws, right? And in this case, we can use the coefficients as our exponents. This is helpful because when we look at the rate law that was found experimentally here, which is that guy, does that match one of the steps? It does match the first step. And because the first step has a rate law that matches the one that was found experimentally, what we know is step number 1 is really our rate determining step, or it's the slow step in the mechanism. So what we know about step 1 is it's actually the slow step in the mechanism. And by default, we should assume that step 2 would be probably the faster of the two in terms of the mechanism. So it really is here step number 1 that's holding up the show in terms of the overall rate of the reaction. And once that one is sort of passed, you know, step 2 should occur at a relatively good rate at that point. Yeah. Yes. So that is basically one of two things that you could use that for, like we did in this example. If we really didn't know which step was the slow step and which one was sort of the fast step, because they gave us the steps and they gave us the experimental rate law, because one of them matched perfectly the rate law that was found there in the experimental rate law, we know for sure that that's a slow step. The second way we're going to sort of use that in just a second is we can determine that if we want to know the overall rate of the reaction, it's really going to be determined by the slow step. So we could use the slow step if we're really not given the rate law. We're going to use the slow step to help us determine what the overall rate law should be for that mechanism. So there's going to be a second type of problem here we'll do here in just a second, where we're sort of given the mechanism and we're given the experimental rate law, and we want to sort of prove that the mechanism is a good one, and where you need to use the slow step to help us do that. So the slow step is really important in mechanisms, because ultimately it is the one that determines really the overall rate law for that reaction, and we use it to either figure out which one's the slow step or use it to figure out, is it a good mechanism or not. Other questions on that? Okay, so let's take a look at another example of this here. And this is a different type of mechanism problem. Here we got a bunch of different steps. So we got 3 different steps going on. We have the overall reaction given to us, which is what we are looking to determine. And we do have the experimental rate law also given to us here. So this is a slightly different type of mechanism problem. This is sort of a problem that I kind of referred to. I think it's like geometry. You do like proofs or something, right? Where you have to prove that it is sort of correct or prove that it's not correct. And that's sort of what we have here. We're given the experimental rate law. We also are given which steps are fast and slow. So we have a lot of the information. So the goal here in this type of mechanism problem is to figure out, is this really a good or bad mechanism? So when determining if it's a good or bad mechanism, remember there's really 2 things that we need to make sure of. The first thing is when we add up all the steps, we get the overall reaction. We get the same overall reaction we're looking at. And secondly, does the slow step have the same rate law as the experimentally determined rate law? So those are the 2 things we need to make sure of. We add everybody up, we get the overall reaction. And secondly, when we actually determine the rate law based on this mechanism, it should match perfectly the rate law that's experimental, and then it means it's a good mechanism. If either one of those things do not work, if you add it up and it does not give you the overall reaction, or you determine the rate law based on the mechanism and it does not match, then it means it's not a good mechanism, basically. Okay. So we'll start with the easiest thing, which is actually we're just going to add up all these equations together and just make sure that we actually do hit, obviously, the equation we're looking for. So let us do that first. So we'll go here and just gonna add these together. Same idea, we're going to cancel out things that are on opposite sides of the arrow. So that's going to go away. I believe this will go away. Let's see what else. We got anything else there? I think that is it, if I'm not mistaken. So what that leaves us is on the left-hand side, we got a couple of NOs. We have one H2 in the second one and a second one in the third, gives us 2 H2s. Right-hand side, we got a water in the second one and a water in the third one, gives us 2 waters, and we have 1 N2. So the thing that we need to make sure of first off is all these steps do add up to what we're looking for. So far, so good on that. Now, we are nicely told in this case, the first step is the fast step, the second step is the slow step, and the third step here is the fast step. So if I want to determine which one is the rate determining step, which one is it? It is the slow step. So that's a very easy way to determine which one is the rate determining step. They will sometimes go, hey, this is the slow step. So because this is the slow step, this is the rate determining step, right? By the way, in terms of intermediates in this case, what are some intermediates we got going on here? We have N2O2, right? And we also have N2O, right? So we got a couple of intermediates happening in this reaction. Because the second step is the slow step in the mechanism, that means when I write the rate law for the second step, it should match the rate law that was found experimentally in order for this to be a good mechanism. So let us write the rate law here for the second step. So for the second step, the rate would equal K times H2 times N2O2. So the goal here is to look at this rate law and compare it to this rate law, and do they match? Do they look identical to each other? I see here yes, and I see shaking of heads no. So that is both answers. It's a good idea to go both ways because you might cancel out the wrongness. So let me tell you, first answer is you can't really tell at this point. The reason you cannot tell at this point is when we look at the rate law for the second step, what do we have in it? Yeah, we have an intermediate. So we're not really comparing, as the old saying goes, apples to apples, yes? So we're kind of comparing apples to oranges. So what we have to do in this case is actually do a little math with our rate law here for the second step to really get rid of the intermediate, so that what we're left with is a rate law that has pretty much everybody from the final reaction in it. At that point, we then can basically do our comparison. So our goal at this point is we want to do a little bit of some manipulation to get rid of the intermediate here in our rate law and do like a substitution. So how do we go about doing that? We go about doing that by using the other steps. So here's the steps again. So our rate law for our second step that we wrote is the rate is equal to K H2 and N2O2. So the goal here is to really substitute out the N2O2. And the only other step where we actually do see N2O2 is which step? It's the very first step, right? That's the only other one where we actually see it. Now, when we look at this first step here, we do see a different arrow here, right? We see an arrow heading in both directions. And that implies that this is a reversible reaction, right? Which has a forward direction going that way and a reverse direction going in that direction, right? So what this means is because this is a reversible reaction, we actually can write two rate laws, one rate law for the forward direction and one rate law for the reverse direction. In the reverse direction, our products would be our reactants, and in the forward direction, our reactants would still be our reactants. So if we write a rate law for the forward step, and I'll just put an F for that, that would give us K is NO, and we would square it because of the 2 that is there. If we write the rate law for the reverse reaction, that would equal K times N2O2. We're going to talk about this in the next chapter, but when you have a reversible reaction and it reaches what is referred to as chemical equilibrium, that means that the rate of the forward direction will equal the rate of the reverse direction. So that is what chemical equilibrium means. And sometimes the mechanism problems, they'll go like fast equilibrium and put that next to it or something like that. But basically when this guy reaches equilibrium, the rate of the forward direction will equal the rate of the reverse direction. That's important for our purposes here because this number here that I don't know and this number here that I do not know, are they the same number or different numbers? They are going to be the same because when this first reaction reaches equilibrium, both of these guys will be the same number. Again, not sure what that number is at this point, but we do know it will be basically the same number. And that's important because now I could actually set each of those things equal to each other. And I could set that the K of the NO squared would equal the K of the N2O2. Any questions so far? Remember that the goal is we eventually want to figure out what this equals, right? The N2O2. I could do that now by dividing this to the other side. And that gives me that N2O2 will equal K NO squared divided by K. The whole purpose of what I just did is now I could take this entire thing because it equals N2O2 and basically substitute it into my rate law up here for the second step. Yeah. Any questions on that so far? All right, so we're almost there. Now that I'm going to substitute that in, that will give me a rate law again for the second step here that I'm substituting in. That is going to get me that the rate is equal to K times H2. And now I'm going to take the thing I substituted in. So I'm just going to write it exactly like it is here, divided by K. Now I have a rate law that expresses what's in the overall reaction. It's a little clumpy looking here. We could do a little reducing down. The top number here is a rate constant, right? That's a rate constant, and that's a rate constant. Are they all going to be the same or different numbers? The same, which means the K on top and the K on the bottom will cancel, right? And that will reduce us down to a rate law for the second step after we do our substituting that looks like this. Now we have actually a rate law that we could compare to the original one that was found experimentally, which now I forgot what it looked like, but let's take a look. It is this one. And according to the experimental rate law, it was H2 times NO squared. After doing our substitution, we hit a rate law that matches. Now we are comparing apples to apples, right? And do those two rate laws match? They do, even though at first they didn't look like they did. Now we can see that they actually do match. And what that means is we hit the 2 out of 2 things we needed. All the steps added up to the overall reaction. The rate law for the slow step in the mechanism matches the one that's found experimentally. All those things means this is a good mechanism or a plausible mechanism. Doesn't again mean it always happens this way, but this is a possible explanation as to how this reaction takes place. Any questions on any of those steps? Yeah. It really does depend on the type of mechanism problem, but in a problem like this where the basic question of a problem like this would be, is this a good or bad mechanism? Basically, is this a plausible mechanism? In that type of problem, it would probably be given to you in the problem. In a mechanism problem like the first one we did, where they're just asking you kind of, what is the overall reaction? What's the intermediate? Which one is the slow step? It wouldn't be given to you. You'd be looking for the one that had a rate law that matched the one experimentally. And much like the first example, right off the bat, once you write the rate law for that step, it would match perfectly. So there's kind of a couple different versions of sort of mechanism problems. Other questions on that? All right, I did one. Now you do one. Yes. All right. So based on this mechanism here, is this a good or bad mechanism for this reaction? And the 2 is way up here. I'm not sure why. So we'll put the 2 over here. So that's the overall reaction. And that is the experimentally found rate law. Does this mechanism, is it good or bad? Take a few minutes, see what you come up with. So again, if we want to make sure that this is sort of a good or bad mechanism, first place to start would be just to add up everybody here. So if we add up everybody, it does look like our O cancels, and I believe that's it. So that leaves us 203 on the left and 12302 on the right. So far, we're good because, again, our overall steps do add up to the one we're looking for. Again, if it didn't, then obviously you would be done at that point. It would be a bad mechanism. We know that the rate determining step here is which step? It is the second step, right, as that is the slow step. So we could write a rate law for that second step. And in this case, it would be the rate is equal to K times our O3 and our O. This again is what we want to compare to our experimentally determine one, but we do run into kind of the same problems we had on the previous one. Our intermediate here is O, and we do have an O here in our rate law here. So we do want to kind of do some math here like we did previously to really substitute out that intermediate so we could kind of directly compare, is this rate law going to match? So to do that, we're going to go here to step number 1 to find basically the way to substitute out that O. This again is a reversible reaction, which means we can write 2 rate laws for this. The rate for the forward direction would be K times O3. The rate for the reverse direction would be K times O2 and O in this case. At this point, we were looking to isolate O, and we can set both of these guys equal to each other like we did previously. So that would give us K of O3 is equal to K of O2 and O. To isolate the O by itself, we're going to divide this to the other side. That will then give us that the O is equal to K O3 up on top and KO2 on the bottom. We now have something that we can substitute into this rate law up here so that we can see if it really does match. And if we do that, we end up with a rate law that is KO3 times KO3 divided by KO2. Again, we could do a little bit of cleaning up here. We have a K on top and a K on the bottom that's going to cancel. We basically have O3 and O3, which is O3 squared right up on top. So kind of cleaning it up gives us the rate is equal to K O3 squared up on top and O2 on the bottom. Now we got something that we can compare to this rate law. Do they match? The answer is yes, they do match because that is O to the -1, which means 1 over O2, right? Which puts it on the denominator. So they actually do match in this case. And that means that this is, for all intents and purposes, a plausibly good mechanism, a possibility as to how this reaction takes place. Any questions on any of those steps? So this is a very common mechanism problem where they sort of give you everything and you kind of have to use the mechanism to prove that it's good or bad. Again, the 2 ways you basically are going to do that, all the steps add up, and when you finally substitute out and get that rate law for the slow step that has just the overall guys in it, you should be able to compare it and see if it matches. Here. All right, one last one here. Determine the overall reaction, the rate determining step, and the rate law, and identify any intermediates in the following mechanism. So we're going to add. In this case, it does look like B will cancel, and I think that's about it. So that's going to give us 2A plus B2 goes to 2AB would be our overall reaction. We would see here that our intermediate would be B in this case. And let's see, we got that. We got the rate determining step should again be the slow step here. And there we go, there we go. And that means the rate law would be coming from that slow step, which would be K times A times B to the 2. Any questions on any part of that one there? Questions on mechanisms or anything about that? Okay. Now let's talk a little bit about, before we move on from mechanism, how we could sort of display a mechanism using like the energy diagram. So if you remember, the energy diagrams are those ones we saw earlier, that has the activation energy and stuff like that. So why don't we steal this one here? So A plus B2, A plus B2 goes to, oops. A, B, and B. A plus B. Okay, and on this particular one, it was, which step was slow? Was it the first one? Yeah, first step was slow. Second step was fast, right? All right. Let's see here. Okay, so if we were to do this reaction, and we'll just call it a, we'll do, why not? Let's call it endothermic overall, right? So the overall reaction, as we saw, was 2A plus B2 goes to 2AB. So if we were to draw our energy diagram for this, energy, we would have our reactants, which would be 2A plus B2, right? Now, the first step here is the slow step. So we're going to have a hill that these guys are going to climb to form our intermediate, which was a B, right? And this is a very bad energy diagram, but we'll do our best here. That is our activation energy for our first step. Pretty big hill, right? And that's because it's a slow step. Now, the second step is relatively quick, right? It is going to be our intermediate, and basically our A and B, they're going to then go to products. So it should end up having a hill that is smaller than our first one, right? So if we kind of rolled this around and came back up, and where we should end, I'll use one of my bad lines here, right there. We should actually end somewhere here, for example. If I did this right here-ish. Now, we have this guy, which is a little smaller here. I maybe could have made my first hill a little bigger there, but it is relatively smaller. So this hill here, I'll just make it exaggerated here, all the way up to here, would be our E of A, which definitely has a much bigger hill than our second step here, which has a smaller hill. Overall, though, our reactants started lower in energy than our products, right? So overall, the overall reaction here is endothermic, right? So that's important. The really badly drawn hill here that's much bigger would represent our first step, which should have a bigger hill to climb. That's why it takes slower. Our second sort of faster step here should have a smaller hill to climb and have a smaller, obviously, drawled activation energy. Question on that one there. Now, obviously, if we did say the one previous, and I'll try not to screw this one up as bad here with my drawing, but we had our O, that was our intermediate in this one. We had our 2O3 went to 3O2 in this case. So we did endothermic on that one. Let's just say that this one, for example, was exothermic in this case. So we'll have our 2O3 here. In this case, the first step is actually a fast step, right? The second step is a slower step. So coming up here and coming down to our intermediate, which would be O, this would be our first step here, which would be our activation energy. Our second step would curve back around and come this way to our O2 in this case. And this would be the hill for our second step. So we can see again a much smaller hill here on the first step, right? Which is why it's fast. A larger hill over here because it's a much slower overall reaction though in terms of energy, right? Reactants are higher in energy than products, right? So we're going to give off energy overall, and this reaction would be exothermic. So you can display using energy diagrams these mechanisms, and basically your activation hills should reflect sort of which one is the fast or slow step. The slowest step in your mechanism should end up being a step that has a much larger activation energy hill than the faster steps in it. Any questions on how to do that? Again, the overall delta H for this reaction obviously is found from the difference between here and here, right? The final and initial is where our delta H for this reaction would be, which would give us a negative delta H in this case if it was exothermic. Any questions on how to display these energy diagrams? You'll get some practice in the next experiment. You'll have to draw some of these sort of guys. All right. So that's mechanisms. So just to kind of finish up this chapter here, we talked about it a little bit earlier, but a catalyst really is a substance that we add to a reaction. And for most part, it is added really to speed up the reaction. There are negative catalysts that can technically slow down the reaction. It's important to remember that a catalyst is not a reactant. It's not a product. And it does not get used up in the reaction. It is still there at the end. It is there really just to facilitate, in most cases, that reaction occurring a lot faster. There are different types of catalysts. A catalyst could be, for example, a metal or something like that, where, you know, for example, what happens is instead of everybody kind of flying around to find each other or moving around to find each other, perhaps they're kind of attracted to that catalyst and brings everybody to a more central location, allowing for a more efficient way for everybody to sort of come together instead of them having to find each other. Everybody's like right there. The result of that is you get a greater amount of reactants coming together and basically an alternative pathway for this reaction to take place. And it usually will happen a lot faster. Ultimately, what a catalyst does when we do look at the energy diagram is it's able to find an alternative pathway for this reaction to sort of take place. The end result of that is it will lower the activation energy. And because the activation energy gets lowered, that means, again, you got a greater amount of guys on the reactant side that basically could get over to the product side, and thus the reaction will occur a lot faster. So ultimately, a catalyst will lower that activation energy, the end result being a much faster reaction in most cases than what you would see in the uncatalyzed reaction. Any questions on that there? So as the activation energy drops, the rate constant increases. Again, the rate constant really, you know, kind of your measure how fast or slow the reaction is taking place. Again, a large rate constant would imply a very fast reaction. A smaller rate constant would be a slower reaction. There are a couple different types of catalysts, and they kind of go like homogeneous, heterogeneous mixtures. A heterogeneous catalyst is one where the catalysts are in different phases. And by the way, you typically do see catalysts written on top of the arrow. So, you know, something like platinum, sometimes H+ is written, which means an acid is being used as a catalyst. Haber process for ammonia. Ammonia is a really slow reaction unless you actually put a catalyst in there. Making of nitric acid or catalytic converters have solid catalysts inside them in our cars. Homogeneous catalysts are guys who are basically in the same phase as everybody else. So those are things where we use acid as a catalyst or base as a catalyst. Like the experiment we did today, we use HCl. It technically really is a catalyst in that reaction. And although it is, we kind of include it like a reactant, but it's actually there to help speed up the reaction and make it happen relatively quickly, which in some cases maybe too quickly. Here's the example of the Haber process. Again, this is typically where you see the catalyst written in the reaction. And as you can see, the catalyst really just sort of providing a platform for all these gas molecules to come together. It also aids in them really unassembling and reassembling a lot quicker in an easier fashion than it would. This is the process of making nitric acid. When you make nitric acid, you know, it's an interesting process, but you sort of make some of your nitrous acid as well as nitric acid, but the nitrous acid actually can then go through and be broken down into more nitric acid. Using a platinum catalyst is needed, as you can see there. And in our catalytic converter, you got a couple of catalysts there and 2 chambers. Helps get rid of all the hydrocarbons as they come through here, and hopefully allow stuff to come out the tailpipe in a clean fashion.